And so 5 minus 2, 3. If this occurs, then we say that's the arithmetic sequence. So in an arithmetic sequence, the difference between two consecutive terms is always equal to the same constant, called the common difference. So I can define an arithmetic sequence recursively. An arithmetic sequence is such that a sub n plus 1 is equal to a sub n plus d for some constant d. And usually we make the restriction that d is not 0. Otherwise, the sequence is just the constant sequence. You don't have to make this assumption, but it's a very boring sequence if you don't. It's be like 4, 4, 4, 4, 4 forever. So it's not a very interesting sequence. Let me determine a formula for the nth term of a arithmetic sequence. So the nth term of an arithmetic sequence has the following formula. A sub n is just equal to a sub 1 plus n minus 1 times d. Let's try to show that this is true using the mathematically. Let's show that the initial case is true. So replacing in here by 1, I get a sub 1 plus 1 minus 1d. Well, 1 minus 1 is 0. 0 times d is 0. So a sub 1 plus 0 is just a sub 1. If I replace n by 1, well, then a sub n is equal to 1. So therefore, these things are equal. They're both equal to a sub 1 when n is equal to 1. So I've shown that this formula is true when n is equal to 1. Let me show that the induction case holds. So first, let me assume that the following induction hypothesis is true. So let me suppose that a sub n is equal to a sub 1 plus n minus 1d. Then I want to show that this formula holds when I replace n by n plus 1. And so let's look at a sub n plus 1. Well, by the definition of an arithmetic sequence, this is equal to a sub n plus d. But by the induction hypothesis, a sub n is equal to a sub 1 plus n minus 1d. By the distributive property, I can factor this out. This is just n minus 1 plus 1. I can regroup this. I can change the order and regroup it. So this is n plus 1 minus 1. But now I see that this means that this formula here works when I replace n by n plus 1. So just replace this n by n plus 1, this n by n plus 1. Then these formulas are the same. Therefore, I've shown that the induction case works. Therefore, by the principle of mathematical induction, I have that a sub n is equal to a sub 1 plus n minus 1 times d for all natural numbers n. Let me define an arithmetic series. And so recall that a series is just, well, a sequence of partial sums. And so it is of a sequence of partial sums derived from another sequence. And so a arithmetic series is a series that's derived from an arithmetic series, a sequence. And so a series derived from an arithmetic sequence is called an arithmetic series. So when Carl Friedrich Gauss was 9 years old, his instructor in class asked their students to do the following problem. Add 1 plus 2 up to 100. And thinking that this would take students forever, Carl Friedrich Gauss immediately answered 5,050. So let's figure out how he did that. So the problem is, I want to add 1 plus 2 plus 3 plus ... up to 100. Well, if you just write that sum in the reverse order, 100 plus 99 plus 98 plus ... to 1, and add them. That's the sum that you want. 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. So you get a whole bunch of 101s. You get 100 of them. Well, but you don't want 100. You want half of those. So 50 times 101 is 5,050. So that's how he determined that the sum of the first 100 natural numbers is 5,050 without having to actually add them all up, which would take forever. So let's do this more in general. Let's find the sum, the formula for the sum of the first n terms of an arithmetic sequence. So let S sub n be the sum of the first n terms of an arithmetic sequence. So this will be the sum k equaling 1 to n of the arithmetic sequence a sub 1 plus k minus 1d. Well, the sum is what Gauss said. You add the first and last terms and then take the total number of terms and divide by 2. So it's n over 2 times a sub 1 plus a sub n. Well, I know that a sub n, the general term arithmetic sequence, is a1 times n minus 1d. First, in terms of arithmetic sequence, can also be given by the formula n over 2 times the quantity 2a sub 1 plus the quantity n minus 1d. Let's show that this is true. So let's show this by induction. So let's look at the initial case. So the initial case is true. And I guess I'll just show this formula is true. If you show this formula is true, then you've shown the other formula is true. So let's replace n here by 1. And so this is the sum k equaling 1 to 1 of a1 plus k minus 1d. So this is just the sum of, well, this is the first term, a1 plus 1 minus 1d, but 1 minus 1 is 0. 0 times d is 0. So this is just equal to a sub 1. Let's plug in n equals 1 here. So this will just be 1/2 2a sub 1 plus n, which is 1, minus 1d. Well, 1 minus 1 is 0 times d is 0. And so this is just 1/2 times 2a sub 1. The 2's cancel, so this is just a sub 1. So therefore, these are equal. And so I've shown that the sum, k equaling 1 to n, of a sub 1 plus k minus 1d is equal to n over 2 times the quantity 2a sub 1 plus n minus 1d when n is equal to 1. So now let's do the induction case. So let's assume the following induction hypothesis, that S sub n is equal to n over 2 times the quantity 2a sub 1 plus n minus 1d. Let's look at the next term, S sub n plus 1. So the sum k equal 1 to n plus 1, a sub k minus 1d. Well, it's going to be the sum of the first n of those terms, S sub n, plus the last term. So a sub 1 plus, replace k here by n plus 1 minus 1d. By the induction hypothesis, S sub n is just n over 2 times the quantity 2a sub 1 plus n minus 1d plus this last term. Let's multiply n over 2 inside the parentheses. So let's do that. And so this is equal to, well, the 2's cancel, so it's n a sub 1 plus 1 half n times n minus 1d plus this last term. Well, I can cancel out the 1's. And so this is just equal to a sub 1 plus nd. Let me multiply the n inside the parentheses. So I just get 1 half times n squared minus nd. I have an a sub 1 and an a sub 1. So I can factor out the a sub 1 to get n plus 1 times a sub 1. Now, I can factor out a 1 half from this. So I get a 1 half d from this term. So this is a d here and a 1 half. So what remains is n squared minus n. I have here a 1 half d, and so I can factor out the d here. 1 half, well, this means that this becomes a 2n. The 2n plus minus n just becomes a 1n. And so I can factor out the n here. So this just becomes n times n plus 1. There's n plus 1 in common. Let's factor out 1 half n plus 1. So this becomes a 2a sub 1, and this just becomes nd. Let's write n as n plus 1 minus 1. But now, the way I've written this is that this formula is the same as our original formula, where I've replaced n by n plus 1. So if I replace n here by n plus 1, this should be n plus 1 over 2, and that should be an n plus 1, which it is. Therefore, I've shown the deduction case works. So by the principle of mathematical induction, the sum k equaling 1 to n of a sub 1 plus k minus 1d is just equal to n over 2 times the 1d. And this is true for every natural number n. Let's do some examples. On page 744, write the first 6 terms of the arithmetic sequence with the given properties. A sub 1 is negative 12, and d is negative 5. So the first term is negative 12, and then I keep subtracting 5. And so, okay, come on, what? Okay, so the first term is negative 12, subtract 5, negative 17, negative 22, negative 27, negative 32, negative 30, etc. 2, 4, 6. So that is the first 6 terms. In this arithmetic, you just keep subtracting 5 to get to the next term in the sequence. Find the missing term in each arithmetic sequence. Find the 35th term of an arithmetic sequence whose first term is 50 and whose common difference is negative 6. So I can just use the formula for the nth term of an arithmetic sequence. The nth term is just equal to a sub 1 plus n minus 1d. And so I just need a very small amount here. Okay, there it is. And so the 35th term, a sub 35 is equal to a sub 1 plus 35 minus 1. And maybe I'll actually plug in those numbers. So a sub 35 is a sub 1 plus n minus 1 d. And so 50 plus 34 times 6 times negative 6. So minus 34 times 6 is equal to negative 154. And that is your answer. And maybe I should write it this way. Okay. Maybe I should just write it like that. Okay, so let me do problem 24. Find the required means. Insert 5 arithmetic means between 5 and 15. Okay, so let's just recall the arithmetic mean. If I asked you to find the average of 6, say the average of 6 and 10, you would say, well, the average is 6 plus 10 over 2 is 8. Sorry, it's not moving. Okay, so it's equal to 8. But what this means is that what I've done is I've actually made an arithmetic sequence. I've written the following as the arithmetic sequence, 6, 8, 10. And so I've inserted one arithmetic mean between the numbers 6 and 10. In this case, we want to insert 5 arithmetic means. So with that, and so we will start with 5. And then end with 15. 1, 2, 3, 4, 5. And we have inserted 5 arithmetic means between, maybe I'll call that A's. This is A1 and A7. A1 and A7. And so if this is an arithmetic sequence, then that means that I've inserted 5 arithmetic means. So I know the general term of an arithmetic sequence is given by the following formula. So the seventh term is equal to the first term plus 7 minus 1 times d. I don't know what the common difference is, but that knowing the common difference will allow me, once I know, and I do know the first term, to figure out every term in this arithmetic sequence. So subtract 5 from each side, divide by 6, and so the common difference is equal to 10 over 6, 5/3. Therefore, the arithmetic sequence then becomes 5, add 5/3, so that's 1 2/3, so that's 6 2/3, 8 1/3, 10, 11 2/3, 13 1/3, and then 15. And so my 5 arithmetic means are these 5 terms in my sequence. Find the sum of the first n terms of each arithmetic series. So this is equal to using the linearity of summation. This is just 3/2 times the sum n equals 1 to 20 of n plus the sum n equals 1 to 20 of 12. So this is 3/2. Well, I know the formula for the sum of n equal 1 to 20 of n. Well, the sum n equals 1 to k of n. It'll just be k plus 1 all over 2. So this will just be 20 plus 1 over 2. I know what 12 plus 12 plus 12 added up 20 times is. Well, that's just 12 times 20. So this is equal to 3 times 20 times 21 all over 4 plus 240. 12 times 20. And so this will just be 15 times 21, dividing 20 divided by 4 is 5 times 21 plus 240. 15 times 21 is 315 plus 240 is 555. So if you add up all these numbers, you get 555. And that's it. And so that's it for